began. I can't begin to know when, but then I know it's going strong. Hands, touching hands, reaching out, touching me, touching you. Sweet Caroline, good times never seem so good. I've been inclined to believe it never would, but now Hello everybody, welcome to this week's edition of Video Notes from Mr. Flugum's AP Chemistry class. That's right folks, this is for AP Chem. Thanks for tuning in you guys. We're going to cover redox reactions and oxidation numbers. So some of this will be review from last year and some of it will be new. Alright folks, so let's talk about redox reactions. This is something you probably talked about in your general chemistry class, but I want to review it so you've got it down. So basically this is short for a reduction oxidation reaction. And when that happens, that means electrons are being exchanged between atoms. And usually those atoms are of different substances. So the substance that gets reduced gains electrons, right? So that means its charge gets smaller or more negative. And the substance that's oxidized, right, that means its charge increases or gets more positive, loses electrons. So here's an example of a single displacement redox reaction, right, where we have a solid iron that is put into a copper solution, right, and when that happens, right, the iron is oxidized because it loses electrons and becomes more positively charged, right? And the copper is reduced because its charge decreases, right? It becomes more negative. In this case, it becomes neutral, but that's because it gained 2 electrons and no longer has a positive 2 charge. So that's an example of a redox reaction. So the big question is this: how do you know what gets oxidized and what gets reduced? The answer is this: oxidation numbers. Basically that just means charges. So how can we tell what the charges of atoms are before and after the reaction? So what we're going to do next is go through some rules and some ways that we can determine these oxidation numbers and determine what happens in an oxidation and reduction reaction. So here's our first rule for determining oxidation numbers. If it's a lone element like these guys right here, the oxidation number is 0. There is no charge on it. Second rule is this: anything that is an ion by itself, all right, the oxidation number is the same as its charge. So magnesium 2+ is a positive 2 oxidation number, and so on. Okay, now oxygen is always a real common element in these type of reactions, obviously by the name of it, I guess. So oxygen is almost always has an oxidation number of -2 when it's in a molecular compound, for example water or carbon dioxide, right? However, there is an exception to that. That is in peroxides. So in peroxides, oxygen's oxidation number is -1. Alright, hydrogen's kind of a funky one. It has 2 different oxidation numbers and it depends on what it bonds to. So when it's bonded to a non-metal, it's +1. When it's bonded to a metal, it is -1. And it can do both. So here's a really important one because this kind of covers lots of elements, not just specific elements. Okay, so when it's a covalent compound, and there's no hydrogen or oxygen. So we've got the most electronegative element has an oxidation number equal to its charge as an ion. So for example, fluorine and chlorine are both going to be -1s because that is their ionic charge, right? They tend to gain one electron. Okay, last thing is this. How do we determine what the other elements are? Because we can begin to determine certain elements, like oxygen's an obvious one, hydrogen, certain ions are obvious, right? And electronegative ones. But how do we determine the rest? Well, the answer is this. The sum of the oxidation numbers has to be equal to the overall charge. So when we have like water, for example, right? Water is a -2, okay? And that means we've got to equal those out because water is a neutral atom, right? So the H must be 2 positives. That way we can do 2 positives with 2 negatives and equal out the charges to 0. Okay, so now let's apply this newfound knowledge that we've gained and find some oxidation numbers. So right here we have phosphorus pentachloride, right? Now, this does not have any this is a molecular compound, right, with no oxygen or hydrogen in it. So how do we begin to determine things? Well, we know this, right? Chlorine is the more electronegative, right? It's a more electronegative element, so that means its charge must be equal to that of its ion, which its ion is Cl-1. So chlorine's oxidation state is -1, and there are 5 of them. So that means overall we have a -5, right? Well, what is phosphorus's charge then? Well, this is a neutral molecular compound, right? So phosphorus must be +5 in order to equal out the -5s of the chlorine. So we've got +5, right, plus 5 times -1, right, and that is going to equal 0. So our phosphorus is +5, and our chlorines are all -1s. So back to our original question here. How do we know what gets oxidized and reduced? Well, we have to look at the oxidation numbers. Now over here on the left-hand side with our reactants, we have calcium elemental, which has an oxidation number of 0, and we have oxygen, another element, which has an oxidation number of 0. Now, if we look at the result of the reaction, we have a compound, calcium oxide, right? And if we look at that, we know this, that oxygen, when it's in a compound, always has a charge of -2. Okay? Now to equal out that charge, because this is a neutral compound, calcium must be +2, which is calcium's natural ionic state, right? Now, what gets oxidized and reduced? Think back, right? Atoms that lose electrons are oxidized, and atoms that gain electrons are reduced. We know it was reduced because its charge got more negative. We know this was oxidized because its charge got more positive. Well, thanks for tuning in, you guys. I hope this helps you understand redox reactions a little bit. We'll be covering this in class and doing a lab on it. So, hope you have a great day. We'll see you on Thursday and Friday. Bye-bye.